Shall we go, Sonia? Hello there, hello everybody, and welcome to a new Final Projects presentation ceremony. Today we have ahead of us two presentations from two of our students. They're going to be very cool and very interesting. So I encourage you to stay here, and of course I encourage you, all of you, the audience, to make questions in case that you have any questions. We are going to, after each presentation, leave some time to Q&A, and me as tutor and the other tutors are going to be making our own questions to the students, but we are also accepting any other questions from the audience if we see they are interesting. So yeah, let's not lose any more time and let's go straight with the first presentation. We have already here with us Pablo. He is a student of the 2023 Batch 1 Masterclass, and he is going to be presenting a project named Starbot's Shop, using OpenCV aligned depth images and OMPL planners for coffee delivery. So hello, Pablo. Can you introduce yourself, your project?
Yeah, hello everyone. My name is Pablo. Today I will talk to you about my final project. It's the Starbot shop, and I will be using OpenCV to detect the barista robot and detect the place where the coffee glass have to be. And to move the arm, I will use OMPL planner from Move It. So can I start now?
Yeah, all yours. You can share your screen and go for it.
Go. So can you see my screen?
Yes, we can see it.
Yeah. Okay. So the presentation is divided in the scope. What are my objectives for this project? A quick diagram of the roles, the topics I create, the nodes I will use. And then I divide the perception and manipulation. How did I detect the barista robot and how I move the arm. And then I have some demo for the simulation and for the real robot. And to finish, I will explain some conclusions, some problems I have, and how I want to improve them in future work. So the scope of my project is to take the coffee cup from the table and place it in the barista robot. And how we will detect the position of the barista robot is using OpenCV. I will explain what kind of filters and image processing I did later. And also my plan is to be able to detect the position of the barista anywhere in the ground. It doesn't have to be fixed, or the orientation also can be changed. At least one cup should be placed in the barista robot, because I have some problem with the planner that I will explain later, and some holes, if the barista robot is too far away from the table, cannot be reached for the orientation constraint. So for ROS, the first is the real sense node, that is the one that get the image from the camera. And from this package, I use 3 topics. The first one is the camera info. This topic provide the intrinsic parameter for the camera, so we can change from the image coordinate to the camera coordinates. And then I have the color topic, that is this image, how the RGB camera see the barista robot. And then I have the depth info from the camera. And this is important. The depth must be aligned with the RGB image in order to be able to detect the coordinates of the hole. And then the node barista detector will process all these 3 topics and will generate a new topic with the hole detected as we can see here in the top, and we'll stream this image to the web server. Also, this node will have a service, which the pick and place node, that is the one that moves the arm, we can call this service to call the holes coordinate, and it will provide the four holes coordinate at the same time. And in the web page, the ROS bridge, there is one topic, the web page that will, when pressing this start button, will start the movement of the arm. And then the pick and place package will communicate with MoveIt and the real robot or gazebo. So for the perception, here is the camera, our setup, the Intel D415 depth camera. And as we can see here, this is the RGB image and the depth image. In the real robot, it doesn't look so good, the depth, but anyway, it can be used if we do image processing. And the hardware is important to set up it correctly. So in this case, we need the RGB image enable, the depth image enable, and both RGB and depth image should have the same resolution in order to be able to align them. And then we can align the image, setting this parameter to true. And in the real robot, the camera provides the depth image using 16UC1, and this format, according to the REP 118, is in millimeters, but the simulation is in 32UC1, that is in meters. So if you are working with the simulation and then have some problem with the real robot, maybe you should check this information to make sure you are working with the correct units. And why do we need the image to be aligned? Is because the depth sensor are in different position from the RGB camera. So if we only process the RGB image and then without aligning the depth image, we will have some error in the coordinates. So this is how the RGB image look and the depth camera, and when we align them, it look perfectly, almost perfect, one above the other. And the black space is there is no information. So here is the important information. And then for the image processing, I use this pipeline. First, a grayscale filter, then a threshold filter with binary filter, and then a morphology to reduce the noise in the image to close the holes that are not important, and then blur the image to smooth it. And then to detect the circles, I use the HUG gradient method. I will explain it later. And I recommend you to use this website, Cloud Vision app, because it will accelerate your debugging time, since you can change the values on real time and see how the whole pipeline change. So this is how I tune my filter and pipeline until I just get the barista robot and the 4 holes. So you can add several filters that are provided by OpenCV, or even you can create your own filters if you need them. Let's go. Here. And for the circle detection, I use the HUG gradient method. That is a function provided by OpenCV. And here I use the parameter 1 and 2 and DP, the one recommended by OpenCV documentation. I didn't change those one, but the one you need to change is the minimum radius of the circle, the maximum radius of the circle, and the minimum distance between circles. So why is important the minimum distance? Let's say we have this image and we want to detect the blue circle, but we set up this number too low, we will have many circles next to the blue one. But if we increase this number, this distance, then all the circles that are near the blue circle will be merged into one, and we will able to find only the one that represent the whole that we are looking for. And then the depth image, we need to pay attention that the optic frame is different from both. So in this case, the C coordinate is pointed forward to the camera. The X one is looking to the left, and the Y is to the right, sorry, and the Y is looking down. So it will be like X in this direction, Y like this, and C to the object. And here we have the barista robot, and we use this formula to detect the X and Y coordinates in the image, in the camera coordinates. This is the optic frame coordinates. And here, CX, FX, CY, and FY are the intrinsic parameters from the camera that we got from the topic, the camera info topic. And V and U are the coordinates in the camera, in the image coordinate frame. So it will be this point right, this one we input here, and C will be the distance that we get from the depth image. So after we compute all this, we can get the coordinates for each one of the holes in the base link frame after using the transform provided by the TF broadcaster. And if you are using the simulation, you should be aware that these two parameters, mean depth and max depth, are not set. And if you don't set these parameters, then the depth image will be black. And it took me some time to fix this. So if you are working with this, make sure you set them in your URDF file for the camera. And then the manipulation. What is my setup is the wall, the table, the coffee machine, the arm, and the cup. And I define 8 steps. The first one is the home position. And I use joint values to define this position. Also, for the pre-graph position, I use the joint values. And for the approach, I use the Cartesian values. It means the Cartesian coordinates. So I give the arm some coordinates in the baselink coordinate system. And then for the retreat also, then I rotate the arm to the opposite side of the table. And then I want the arm to go down close to the barista robot. I have the idea that if the arm is near this position, then when it's moved to the hole, it doesn't need some constraint because I guess it's very close to the position, so it will be easy to calculate a solution. But I was wrong. If we don't use some constraint, then the arm will behave like this. So here is going to the hover position, and then it will rotate all over the table, even when the goal was just a few centimeters away from the current position of the robot. And then I decide to use orientation constraint, and for that I follow many tutorials and guides and documentation to try to set up the constraints correctly. As you can see, I set up many planners. I didn't try all of them, but I tried at least like 5 or 7 of them. And they didn't work very well at the beginning. They have a lot of problems. First of all, we are not interested in the C-axis tolerance in this constraint, so we can set up a very not how to say this very relaxed in order to the planner have a better option to plan the optimal way. And then we need to set up this joint and increase the range in the planner. I will show you this later. And I had the problem, even I set up a 10 second time to plan, but also try different like 60 second or 100 second or 120 seconds. And every time I had the problem that sometimes the planner will take too long to find a path. And at the last moment, like here you can see at 10.0075 seconds, it found a goal, or 10.0051, it finds again a goal, but actually these were not real. I will show you later. But when the planner actually found a goal, I discovered it was really short time, like less than a second, 4 or less than a second again. And I guess this was because the way does it work, I used RRT because it was the fastest one, is random. So I thought maybe I'm not lucky sometimes and it goes some way that it cannot find a path easily. And when I set up like this, you can see here, if it says 10 second point something, the arm will move to a location that is not the right one. So in this case, it will go up and then release the cup. This in this case, I set up like 60 seconds maybe for the planner. So here is moving, and the up goal is this hole. So it will go up and release the cup and go back to the home position. That is not the correct way, or not the expected behavior, even though it says it found a valid plan. So my solution was this. If the time is more than 10 seconds, it's not a valid path, and if it's less than 10 seconds, is then a true path, because there is some setting to find if the movie planner return success or not. But even in this case, I receive a success value as true, and it was not working. So I decided to use this approach to fix my problem. So this is the result. So it moves there, release the cup, and then come back to the home position. And here's the demo for the simulation. In the simulation, it cannot grab the cup. I think I need to improve the effort controller. And if you can see in the simulation, I delete everything that was not necessary because I wanted to increase the FPS and computation time to try reinforcement learning, but I didn't have time for that. Okay, and for the real robot, I have a video. We can go to the website and try it. I don't know which one is better for you, Alberto, or we can do both.
Sorry, can you repeat, Pablo?
For the real robot, I have a video, or we can go to the website and try.
Yeah, I would try
But I
the
need to set
demo
up.
live.
Okay. So let's go to the website. Meanwhile, you can see the video because I need to compile, install some package. Yeah, so the website just has a start button and the feedback from the camera.
And do you need to have the cup in any specific position, or how are you dealing with that?
Yeah, this the starting position of the cup must be fixed in this rows inside the sticker. We are not doing any kind of perception for the initial position of the cup.
Okay. We had Rodrigo
Yeah,
there.
it takes some time. That one, yeah.
Okay, so now it's processing the information from the holes and so on, or
It's planning the path to the hole. Sometimes it takes long time, sometimes it's fast. I think that is because of the RRT random exploring.
Now it's going.
The video is not moving because I am on the website, by the way.
Yeah, well, it almost finished, so.
By the way, how can I connect to the? Now I can connect. Okay.
Yes, maybe you can show us already your screen, and we can see there what's going on. Okay, so now you are connecting to the real robot live.
Yeah. Can you see the web browser or just the presentation? Change.
Okay. I see that we already have a cup there in the logo, so we should be good to go.
Go to my GitHub. I have the instruction here for this. Okay, first I need to install this for the web server, for the video server.
Okay. Well, that's quite some terminals.
I think it's like 4.
Okay. So meanwhile this is installing, I'm going to take the chance to say that we are working on a system so that any package that you install through apt in a project is going to stay there. Okay, so you will not have to reinstall it like you are doing it now.
Or maybe just Dockers.
Yeah.
Maybe a good solution.
Yeah. That would be another solution to put everything into Dockers. Yeah.
Yeah, but also Docker is not installed here, so you need to add the install.
Okay, it shouldn't take much more to install. Okay, so there you have launched Move It, right?
Yeah.
Well, Move Group. Now we're for visualization.
Now the barista detector.
Okay, so this is the perception node, let's say.
Yeah. And this is the pick and place.
Okay. So here is where you interface through the Move It API, right? To create all the plans and everything.
Yes, that's right. Here we have the detection node. And then we need the web page. the video server. And then we check the website.
Mm-hmm.
What is, no. Okay, yeah, we need to go back. Okay, the front end is not so creative, but I'm not
Okay.
good at that. So
We can see there. That's nice.
yeah, so now we can detect 3 holes. I hope it works. We click start. We can see which one. Let's put, yeah.
Okay. We can see there Rodrigo checking that everything is good. Okay. So you first.
Okay, see, we
Yeah.
have this problem. 10 seconds, it says, but it's not working. So I replan again until a solution is found in less than
I see.
10 seconds. Yeah.
No. Okay, yeah, so we can see that it left the cup there.
Yeah.
Okay, really cool.
Yeah.
Okay,
Thank you.
so okay.
And these holes are too far away, I think, for the arm to reach it with the constraint, like going totally vertical. So it cannot. Also, I don't know why this one, it may be too close or to the table. I'm not sure why it doesn't work, but some of the too close and too far doesn't work very well. So that needs to be improved. So if we go back to the presentation, or
Yeah.
yeah, okay, I have this one. Yeah, it's the same. Just the first one was with the cup in this orientation, and then I tried with the cup. Oh, rotated. Yeah, pointing this way. So to prove that it can be rotate or move a little bit the base. And this is the problem I was talking. Sometimes it cannot reach these holes too far away. So it will always time out, even though I increase the planning time. So I think the problem is with the constraints are too strict, or the robot, barista robot, is too far away.
Yeah. So for sure there is like a zone, let's say, where if you move the barista robot out of there, then it becomes impossible for the arm to reach that pose.
Yeah. And the conclusion is that it's possible to locate the barista robot coordinate using the depth image information and the RGB if they are aligned, and it's possible to set some constraint to move the arm without flipping the cup and spilling all the coffee around the robot. And it works well in the simulation. And just a few parameters need to be changed in order to work in the real robot. These parameters are the one used for detecting the circle in the minimum radius and maximum radius, because the RGB image resolution were different. So this need to be changed. And for the future work, I want to use reinforcement learning to control the arm and keep the cup stable. And I want to improve the planner so it can reach more quickly the optimal solution. Yeah, that's all. Thank you very much for your attention.
Okay. Okay, so you can stop sharing if you want, Pablo. Then thanks a lot. Very cool presentation, very interesting, very well structured, everything, let me tell you. And also very nice to be able to see the demo live and working. So yeah, now it's time for the questions. So I'm going to ask everybody to share their questions in the chat, and I'm going to be picking some of them to share them with Pablo. I'm going to start with my own questions. I have some noted here. First of all is, I was very amazed by this Cloud Vision app that you shared in order to tune the filters and so on. So how does this work? I mean, is it changing the camera parameters live? How are you interfacing this with the project, for instance? Can you explain a bit more on this?
Yes. I take an image. I save an image using a node, and then I just upload this image to the website. It's not live.
Okay.
Yeah.
Okay. But then using that real image that you take from the real lab, right? Then you can get already the values that you are interested in. Okay. Super cool.
Yeah, that's right.
All right. Then another question that I have here is: did you set or did you play with the joint limits in your moved package? Or you?
No, I didn't change them.
Okay.
Just by default.
Okay. So that can be also as a suggestion. Okay. So playing with the joint limits. There is a file there which is jointlimits.yalm in your moved config. Playing with that can also be very helpful in helping the planner to find solutions. And also, for instance, it can be very helpful in making the planner not make stupid things like you showed at some moment, that it had a goal just a few centimeters far away, and then the robot started to do all this just to reach a goal which is just at the side. So it can be also helpful in that sense, so that setting the joint limits and playing with that. Okay.
Yeah. I will try that also.
Yeah, but very cool also, because you this way you have you investigated and you learned also another thing which is also very useful, which is to set the constraints and so on. So yeah, very good. Okay, I have some more questions, but let me move quickly to the chat to see some of the questions. Okay, so let's start here. I can see a question by Girish. He says, which planner did you find to perform the best out of all the planners that you used?
RRT. RRT Star. Star, yeah.
Okay.
It was the fastest one.
Okay, so in this case, I would say that not the best, but the fastest, probably. Which
yeah.
And in this case, you
the other one didn't provide better solution. Also, the same kind of movement. They didn't provide any shortest path when trying to place the cup in the hole. But it will take more time.
Okay. I have another question here from Rodrigo. Let's say, how would you change the physical environment so the constraints you mentioned don't block the robot from reaching every barista cup hole?
Because the constraints are just orientation, not position. So what the arm cannot do is like flip the cup going to the pitch and yo, maybe is that the name? But the position is not constrained to anything. It can go reach any position it wants. Just set up some orientation constraint.
Yeah, but still, probably, for instance, if the robot moves a little bit away, let's say, then there are still going to be physical constraints in the sense that the arm is not going to be able to physically reach, for instance, one of the holes which is too far away, right? So.
I tried to set up a plane also, but it didn't work. So the best one was the orientation constraint for me. And that's why I also tried to set up the arm in the middle of the barista robot or at the beginning, yes, not far away.
Okay, yeah, that's one of the questions I had noted there. That because I saw that you first go to the middle of the barista, and then from there you go to the hole.
Yes.
So that is why. Can you repeat?
Yeah, the reason is because the planner works better when it's close to the holes than when it's far away.
Okay. So you go to an intermediate position, let's say, and then from there, generating the plan to the hole, it's much easier.
Yes.
Okay, this I think I know the answer, but let me make the question anyway. So, how do you pick the hole to put the cup in? Is that random choice, or do you choose the nearest hole?
I choose the nearest. The hole detector node calculate the nearest point to the base link and provide that one as first, and then I just take the first. And if it cannot reach it for some reason, it will iterate in the others in the other three holes.
Okay, so the nearest point to the base link of the arm, I understand, right?
Yes.
I can see some questions here, like for instance, reason for choosing RRT, this because it's faster, basically. So we already answered that. I can see here. Okay, let me check the question of. Okay, so we have a question from Lucas Gandara. He says, how far do you think is it to use this in a real world environment in a real shop? Provide your opinion once you've worked with the state-of-the-art manipulators. So, okay, so this demo is very cool, and we can see that it is possible, but do you see, how far away do you see this really being deployed into a real cafeteria, let's say?
I have seen this in Korea working by themselves. This same arm, same coffee machine, but the coffee was very expensive, so nobody used them actually.
And also, I don't know about this, but I don't know about this particular case, but usually all these arms that I have seen so far that do this, they are not really using ROS. Okay, so they use hard-coded trajectories, if you know what I mean. Okay,
yeah.
so they have some predefined trajectories to do everything, and that's it. So it's not really that they are using ROS like in your project. You are using ROS and you are planning motions on the moment, and you are doing real perception. So it's not everything hard-coded. Okay, so usually these arms that we see out there, usually, okay, I don't know, maybe there are some that are using ROS, but this is something also to a difference with your project, let's say.
Yeah, that's right.
But do you see it happening anytime soon to have these kind of arms or projects like the one you did in real environments?
Yeah, they can work, but they will need some human supervision, I think. At least one person working, not a fully autonomous coffee shop. Must be someone like checking that the arm is doing well somehow, because they will have some problem. Like maybe someone will block the path by mistake. So there must be a staff, maybe not looking the robot 24/7, but checking some, supervising the robot. So yeah, I think it's possible.
Okay, cool. So let me go with the last question here from Rodrigo. How would you reduce the time for finding a solution in the last step to place the cup in the hole? The last one. Well, so when you go from the center of the barista to the hole, which sometimes we see that it takes several seconds. So how would you improve that process?
I set up 10 seconds, but in my experience, it was usually less than 10 seconds. So less than 1 usually, 0.16, 0.15, or 0.11, something like that. So I will decrease this time to maybe 1 second and just restart the planner every 1 second. So it will try more times and spend less time in solution that already doesn't work.
Yeah, that's an option. Yeah. All right, Pablo. So thanks a lot for your presentation. I think we can leave it here. Very interesting.
Okay.
We have many questions here in the chat, but yeah, we have to already keep moving. So yeah, thanks a lot, Pablo, and see you soon. Very, very good job.
Thank you, everyone. Bye-bye.
Applause. All right, so we have finished with Pablo's presentation, but let's move already with Rómulo's presentation. Let me see if he can join us now. Let's see if we can have Rómulo here. He's coming. We will have him in a moment. So Rómulo is a student from our 2023 batch 2 of the Masterclass, and his project is going to be based on the trash table robot. So we are going to move now from a manipulator arm to manipulator arm to a mobile arm. We stay in the cafeteria, but cafeterias are not only preparing or serving coffee, right? There are many more things to take into account. Like, for instance, we need somebody to be cleaning the tables. So in this case, somebody who is going to be cleaning the tables when the customers leave their tables, this guy is going to be an automated robot, which Rómulo has been working with, so that it is able to automatically detect the table and take it out of the cafeteria to clean it and so on. So I think that we already have Rómulo here. So let me see if we can say hello to Rómulo. Hello there, Rómulo.
Hello, everyone.
If you can open your camera so that we can see you.
Of course. Yeah. Shit.
Okay, there we
Can you see
go.
me now?
Yeah, we can see you, we can hear you. So yeah, it's all yours, Rómulo. You can start with your project presentation.
All right. Let me share the screen first. Window tab entire screen. Can you see the screen right now?
Yes, we can see it. Yep.
Okay. So, as Alberto said, we are talking about the Cafeteria Trash Table Robot project. Um, in this case, we're gonna be talking about the 6 topics right here: table detection algorithm, the robot deployed, sensor and data available for the recognition of the table, environment recognition and navigation of the robot, user interface, and demonstration for the final case. So, do you know that restaurants generate about 32 billion pounds of trash in 1 year just in the United States, making the waste management a huge challenge for the industry? So, for this reason, we are developing this project that takes care of the trash management in a cafeteria or in a restaurant. The project is not limited for a specified business or place. You can use it in a restaurant or in a cafeteria or any other place that you want to use the robot. So, what are the advantages of using a trash management system like this? Well, in a business, you will reduce the accumulation of trash over the time in the space. So, in the cafeteria, you will have the automated system in charge of the trash, and there will no accumulation of the trash in the place. Increase the staff productivity and reduce the laboring costs. So with the last 2 points, we are increasing or making better the customer service. So you will offer a better customer service to your clients. Okay. So these are the two robots used in the project. The first one is the used in the real, and the real one is the chargeable form with those dimensions and specifications. And for the simulated one, we are using RobotNet RB1 robot, which is a little bit heavier and a little bit faster. Uh, well, let's keep going. So, what was the problem with this problem of, let's say, this challenge? The challenge is that we only have one data available for the recognition of the table. So we are just using an RP A1, which is a type of rotating laser range scanner used for creating maps, performance navigation, detecting obstacles, robotics, and autonomous systems. So with this sensor, we only have range data available to identify the table. So I have to manage myself to find a way to identify the table in a place. So how did I handle this situation? You can ask right now. What I did to identify the table when I just have scan range data available. So first of all, I limited the data because I don't want the noise data in the algorithm to process. So I used the from the raw data of the sensor, I extract the X and Y coordinates for each range in 60 degree in front of the robot, just in 60 degree in front of the robot. The other data, I just don't use it. So I use k-means, which I be explaining later what it is, and I input the data of the raw data in this algorithm, and make this is the first filter. After this filter, I use another filter, and it's a second one, and it's a little bit simpler. And I use Euclidean distance from one point to another to identify if the point is too far or too close of the one of each other. So after this, I combine. With combine, I'm referring to for the last 4 points, which let's suppose is the last points of the each table legs, I make all possible 4 points combination in for lately verify which of these combinations meets the table dimensions. So after I identify the table, if those points meet with the dimension I firstly determinate, I localize the table from the robot and from the table to the robot and with the map. So let's jump to this Jupyter notebook where I'm going to be explaining or showing the algorithm a little bit better. Here we are have a first example of how it works, the k-means. So, and the K-means is a popular and supervised machine learning algorithm used for clustering data into groups based on similarity. Okay, so I'll be running these scripts. So you, I make some notes because I'm sharing this notebook with you. So if you want to make some configurations and anything you want. So first of all, we are using those libraries of Python, NumPy, Skylert, once we localize the k-means algorithm, and matplotlib to plot the data we're using. First of all, we import it. Here are some examples of how to install it in your own. Okay, it's connected. Here we have a set of data generated with NumPy, random data. This data is from 0 to 1 randomly. And after this, we just plot it. And this is how the data is visualized in X and Y. So you can see the data is dispersed in the space. So we were gonna find how to relate one with another, of how to divide it. Okay. Once we have the data, we run the k-means algorithm. Okay, is run, and lately we can have this result. In the result, as you can see, we have 4 clusters. Those 4 clusters are the reference of the center point of each group. As you can see, we have 4 groups: the green, purple, the blue, and the yellow one. And the center point of each point is the red star in each point. You can see. So you get from this algorithm, you get an array where it specifies for what group each data correspond. Let's say the first data corresponds to the group 3, for example. And this is how you can know to which group um, does the cluster uh, belongs. So, okay, now let's try the algorithm with the table. As you know, the table we are using right now is a square table, square with the same length in every side. So a square have the next 3 basic formulas: the area, the perimeter, and the diagonals. You can calculate these properties of of a square with these formulas. Once again, we are importing NumPy, Matplotlib, and intertools. Intertools is the new one right here. With this library, we are making the permutation that I'll be explaining lately what it is. This is what I was referring when I said combination in the slides. So let's import it. Okay. This data is real data collected from the real robot. So after after a few filters, and let's say these are clusters data. So I mean that these are the coordinates for each point data. Okay. So after this, we are going to plot it again. As you can see, it figured like a square. It's a little bit like a rectangle, but if you can see right here, these are very small difference in the length or longitude, distance, sorry. Now we calculate the Euclidean distance area as I mentioned before. And right here is where we make the combination or permutation, let's say, for each point. And here we define the dimensions of the table we want to find. And this must be changed for each table we are using, and have to need to make a little bit of test to make sure you are identifying the table you want. So what is permutation? Permutation refers to an arrangement of objects in a specific order. So the permutation of our number is a total number of ways that you can arrange those four numbers. For example, this is the formula used for permutation. And the permutation of 4 is 24. That means that you're gonna have 24 different combinations for four numbers. Okay. Right, this is just a comment. And now, for each combination, we are be calculating the distance between each point. Let me from this point to this point to this point from the other one, and like that. And the diagonal distance to make sure that is the table we want. Lastly, we call again the same function, but this time with the plot, and this is how it works. As you can see, I have 16 combination that meets the dimension I want. Just 16 and not 24 because we have 5 points, and there are some combination with other points that did not meet the dimensions I wanted. And yes, this is how works the comments and the filter I be using. And after I have this the table reconnection or identify the table, then I localize. Okay, can you see my screen? Yes, I think I can.
Yeah, yes, we can
Then
see
I
Rómulo.
okay. Then I localize the center table from the table from the robot and to the map. We're gonna see now an example of how it works. This right here is the transformation of the robot, and as you can see, sorry, these are there are transformation polished for each table legs, one for the center, one for the middle, the center point between the two front legs, and another one is like a pre-approach or approach distance. This is how it works. So I make the robot go first to the approach distance transformation, then orientate to the table middle and move underneath the table until you get into the table center point or transformation. So I make an example right here. This is how looks all the data in process of the table identification. As you can see, this is the raw data you have. This example is for the simulated one. As you can see, you have the wall behind, the 4 point for the table, and another point here. And with the k-means algorithm, we have the cluster for each table leg, and then we filter out all the other points, and finally we have this trajectory calculated for the center point. As you can see right here, there is an error because if you can notice, this data is mirrored from this one. It's like this point is this one. This is because I made a mirror of the data to have a better localization. Okay, I hope this is understood. And the purple triangle is the robot lidar transform. Okay, so the working environments are the construct Starbot Cafeteria located in Spain, and the construct Starbot Cafeteria simulation. First of all, I have to work a lot here in the simulation before I start working with the real road. And so let's keep going. And yes, for make this project work, we have to set up nav2 navigation, and I use DWB controller and the nav planner. adaptive Monte Carlo localization, cost maps, and plans. To generate these maps is the real one of the cafeteria in Spain of the construct. As you can see right here, we have already the keep out zones. These keep out zones are the zones that I don't want the robot to plan through or the robot avoid. So this is a very simple steps. And in the nav 2, I made a few configurations for velocity, orientation, and other things. Because of when the robot move, the table needs to be disabled. So I have a little bit of trouble with that, but finally I made it right. So I developed a strategy to make the robot work better because uh, robots are autonomous, but if you want a simpler and robust program, you don't. I think I don't want to leave all the work to the robot. So what I did was to identify the few positions where I think or thought that the table could possibly be. Why? Because as you can see, you have a whole map, but the table can be right here, can't be right here in the furniture or down the table here. The 6 possible positions I identified that the table can be are those marked in red squares, but for the demonstration, I just worked with 2 positions. And in the simulation, I worked with one because of time, because the simulated process took me like 5 minutes. I don't want to take too long presentation. So the robot start here and go to the table, then retrieve the table and go to the back room. So you will not see right now. So I think this is very important because you don't want to waste time and energy battery in the robot. So you can define a few logic or strategy position for the table and make the robot just look in those positions and save time, save money, save uh, battery. It can be more precise in that way. Yeah. Uh, we have I have worked in this project in Docker, so I'm making this slide you can scan this QR code and follow the instructions and build this project the simulation on your own if you want, and you can modify it if you want. And I'm gonna show you uh, faster. Here is the Docker running and the container. I just run the simulation. I just want to show you. Yeah, you have already in this GitHub the whole project, and you can just uh, make whatever you want and run my code, my work. It's just simple. You just have to follow the instructions that are here. Let me show you where. This is the Docker file. When you build it, you just have to follow these instructions to make it run your own. When you run it, you will have the next. Okay, the next. I will show you in a few moments the next result. Finally, I built and designed a web app where you can see the features of the project, and you can start and control the project too. This is a very simple interface because it needs more work, but you can do the basic thing in here. So this is the Docker file running. You can do it on your own. I'm gonna to move a little bit forward. Well, you can see right here the robot start moving. As I mentioned before, the robot is very slow because I want it to be more precise with the table lifting, and that's it. I'm gonna advance the video a little bit. Well, I will show the whole video. As you can see, the map from the cafeteria simulated is different from the real one. Uh, That's why I try to make this specification right here. This is the cafeteria simulation map. And these 4 points you can see here are the tables legs. You can see there where the robots start publishing the transformation. It sometimes got a few noise data, but faster. It rapidly overcomes and fixes the problems. As you can see, the robot is trying to approach the first transformation. This is a video, just so you to know. Right now, this is stopped because it took a little bit of difference in the position it wanted and lose the. Okay, I am. Okay, right now is continuing to work. Once the robot is in the center point of the table, it just stopped, leave the table, and then retreat the table a few meters behind, and then it has to go to the back room right here. See, it's moving the table. As I mentioned before, I always try to have the robot and the system to work better. So what I did was to set a goal in front of the table, then orientate the robot uh, with a goal to the table, then make another goal past the table, the door, another goal past the door, and finally the last goal where I want the robot to take the table. I make this approach to help uh, the navigation, because if I just hand a goal back to the back room right here, it will take the whole plan, the global plan, continuously, and sometimes it can stuck here. So I decide to help it a little bit and just make like a few steps goals to a better performance. Right now, it left the table right there. Then he comes back to the home position. The idea for this behavior is to, if you have different tables like this one, and you just want to take over one table and move it to the back room because it's full of trash, you can still using the robot to make another um, picks pickups of the table. So, for example, if the robot, when the robot gets here, if you have the dashboard, the interface to send the pickup for the second table, you just have to move to the second table. Or if you have 3 tables, it will be available to work every time you need it. I will advance because once you get here, it ends. This is just for the demonstration and the simulation. So, okay, let's keep going. Okay, this is just 2 pictures for the environment and the robot we are using. As you can see, this is how I can see the environment in Spain from my location. And we have 2 cameras, one to the whole place and one to see the robot approaching to the table in this way. So this is the real place we were working with, and we are going to see it right now. And I'm going to connect to deconstruct right now. This is my project. I was connected, but due to an inactivity, it locked me out. Okay. Let's now connect to the robot. Okay, now we are connected to the robot. We need this. Right. Let's open the terminal. Right. As you can see, I need to install scikit learn for the k-means algorithm, and I need a few more terminals for the HTTP server and other things. First of all, let me prepare the robot, because right now it's in charge station. So let me just make a first topic discovery. Okay. Elevator, in any case, we need to elevator nodes. And I could have just make a launch file to launch all the things, but I did not have the time. This is for the server, HTTP server. Okay. All right. Let's now lower the velocity of the.
Yes, we don't want to crash it.
Yes. Okay. As you can see, the robot is in the center. You can see the center position in the cafeteria. So let's first of all try to connect it to the. Okay, we have this. Connect it to the web page. Entry HTTP server. Have it. Now we need what is the path planner? Interface. Here we have a few nodes.
Okay. So you are starting navigation, right? Or
Yes,
Mhm.
but it takes a few time, a little bit time to load because of the graphical tools. But if I stop it, launch it again, it will launch it immediately. Yes, we have the map here. Yes,
Mhm.
and the nodes, the script. I need to launch this one. Okay, cool. Now, right now, it is just waiting me to give the signal from the web page. So
Okay.
let's open the web page. Oh, okay, I need to do something before. Need to provide the control.js with Rose bridge. Yes, need it. Controls. Okay. Need to reset it. Ready. And now I get the web page address. Good. There we have it. Okay. This is the web page I designed for showing up the Trashbot Cafeteria project and examples I can give and the technologies I used. I also described the robots used and the system factories. This just is a simple web page, just to examples in this case, but it can be improved and make a lot of things right here. And then we have the control zone, which is this one. As you can see, if we expected, it is already connected to ROS. So right here we can do several things, but it is just configured to start the process and to teleoperate from here. Okay, so let's okay, this one. Let's see first the teleoperation. As you can see, I'm moving the robot right now from the web page. Okay, so I'm trying to move the robot to the start position. Okay. Yes, this is the start position. Okay, good. Now, when I press start, it will start the process. The first thing he's gonna do is to move to this place right here, looking for a table that there is no table in there. So just to exemplify, and that it can look for different positions, and in the if the table exists or not. So first he's gonna be here, then he's gonna go to look for that white table right there. The only thing right here is if the robot, the laser can detect the four legs, it will not work. That's you can ask right now, but how does the project will not work? The thing is that this table must be modified to make sure that it always find it, or the table must be rotated. As you can see, the table is rotated a little bit right there. This is this I was the one who made it in that way because I need the robot to visualize all four legs. If there is no four legs for my um, algorithm, it will not work. But I know that it can be improved if I make the recognition for a triangle and not for the square, because it still have the same properties in diagonal and two sides with the same length and three legs. So it can be improved. Okay, let's start it. Okay, I don't know what happened. Great. No, great. Oh, okay. Let me see. Okay, try it. Does I have yes? Oh. Let me try again. If I launch again the server, try it. Start.
So what should he do? What should the robot do now?
The robot should first publish an initial position and then start looking for the table in this position and then in the position of the white table. But for now,
You can try
I don't know.
restarting everything if you want. Let's try to restart everything.
I think it could be. Let me see. Okay, let me make roast to topic and call first. Echo. I need that. Okay, the web topic is not being published. So let me see in a fast way what is happening. So web commands, web page. launch this one. Okay, I'm in the wrong. This one. Right now, just ready and wait to operate. Yes, now there will be no problem because right now I have the topic. Okay, so script is ready, and let me close this too. Server page address once again. Good. So try it. Start. Okay. Right now, as you can see, it start. Now he will look for the. Let me expand this. He will look for a table in this position right here, aiming to this wall. As I specified in the previous strategy map, it will look if a table is in this position. That is a possible one. And this is a possible one too. But for the real robot demonstration, just made it for 2 position. As you can see, it's rotating and look for 1 position. As you can see, the blue data range, the blue range data is the limit data for 60 degree. And just in this area, it will examine it or try to localize a table. Right now, he is looking for the second position where the table can be. Right. Right now, it's just watching 3 legs, but okay. He had 4. See, start moving to the first one, transformation, which is 50 centimeters from the front legs, and then you can see here. Okay. Now the robot lifts the table, and now he will retract it, move it back.
And this retreat is through navigation, or it is just hard coded?
No, it's hard coded. It's
Okay,
just
okay.
a retreat for about 10 seconds and a specific one speed, linear speed. Oh, all right. As you can see. Let me try to help it. Okay.
So here you are doing also the same that you explained for the simulation, that you are sending one goal which is
Yes, it's the first
close to
one
the
got it wrong. I don't know why it took too close to the door.
Mhm.
But and the second one is in the center of the wall on the wall door, and the third one is right there when it finished right now. Just 3-way steps. Once it reaches the last step point, our goal. It left the table. I left it right there to visualize it, and comes back to the home position as in the simulation. Sometimes the road gets stuck right in that way. I think it's for the odometer, but in a few seconds it get out of that like that. He's now returning to the home position. Yes, and that's it. It ends right there. And this is the full demonstration. So let's go back to the presentation right here. And now we're going to talk about, lastly, for the future improvements. And as I first one is mount a user-friendly map in the web to visualize the robot position. That's why, because when you have this in the, let's say you have a touch screen in your restaurant or cafeteria, you don't know where the robot is right now, what it's not doing. So you can have a map that you can visualize where the robot is and what it's doing, if it's moving, if it's stopped or anything. Okay, so let's keep going with the create. The second one is to create web parameters to allow the user to identify other tables. Yes, this is because we have this layout. Okay, but you just can't to start the work as we did before. But if you can have a few other buttons right here to specify, let's say, position one, table two, table three, and have the state for each table if it's in the background of it in place. And that's the thing I like referring to with the second improvement. And finally, to integrate weight sensor to the robot to be able to measure the pound of trash. Why? To have data of how much trash is, let's say, um, managing the system, or how much trash is generated in the cafeteria and things like that. Is to have a feedback of the process of the system. And yes, that's all. And if you have any questions, anything to comment,
Okay,
I
Rómulo. So,
can hear you.
hello, hello. Yeah,
No,
thanks.
yes.
Thanks a lot for your presentation. Very cool. So yeah, we are now in the audience's preferred section, which is the Q and A's. So you have the chance now to make the questions. So I'm going to start first with my own to give some time for the audience to write down yours. So okay, yeah. So first question is, you said that you selected this k-means algorithm for the first filtering of the points and so on. So, uh, um, did you think about others, or why did you decide to use k-means, or did you thought at some point about using other algorithms, or no, or
Honestly, I make a research of a few methods. Even I thought others say um, well, teammates, let's say, of the construct friends presentation the way they did. So I tried to make a different method to not just use the same that we used before to present it. And for my opinion, this was the simplest one. and the simplest and at the same time the robust one. It can be a lot better, but yes, I prefer to do this with k-means because of the type of data we have, and I thought it would be a lot easier to do it with k-means.
And in the same direction, so you said that right now your algorithm has a limitation that it needs to detect the four legs to work,
Yes,
right? So you also mentioned that you can change that to try to detect a triangle instead of a square. So this can be done with k-means also, or you will need to
yes, of
change?
course. Of course, you can do it with k-means because you will have the same clusters. You have a cluster in each legs. So you will have four clusters, one for each leg. If you have, if you can see in the demo, let me just screen share again. But you will have the same clusters. You just have to analyze and modify to use clusters like that. Just three clusters in not. Right here we can visualize it. Yes, right here. You can see right here, each red star is a cluster of each group. Okay, so right here we have four clusters, five clusters. What I'm doing right now is making combination of 4 points, and for those 4 points, analyzing the dimensions. If it meets the dimension, then it is a table. So what I can do, I can eliminate this one, and then meet, make combination for 3 points and analyze if dimension meets with the table. So I can analyze the leg of the 3 point, the leg from point 1 to point 2, the point 2 to 4.3, and analyze the diagonal from point 3 to point 1. Those dimensions are the same for these three other points. Let's say point 1 here, point 2 here, point 3. Like the table is a square, you can determine that is the same. But if the table is not a square, you can do it like that. Is it clear?
Yeah. It answered my question. Yeah. Okay, so let's go with other questions. Okay, I see this one because I also had this one annotated myself. This one is from Rodrigo. He says, I see the movement of the robot is quite wobbly once it has the table on top. So when it had the table on top, the robot was like doing strange movements and he says, is this a nav2 teleoperation thing, or is this a problem of the robot hardware that it doesn't move smoothly? Let's say.
Honestly, I can say it's a difficult question because I am not in physically in contact with the robot, and I cannot visualize the bottom of the robot, and I can't visualize how are the wheels of the robot. But I can note that when you advance and reduce, let's say, move back the robot, it have a little bit of, let's say, inclination, or how
Yeah,
can I say this
yeah.
one?
I understand.
It move a little bit like this, and but honestly, it can be managed with a slower movement in nav2 and a lot of configuration in the acceleration and deceleration of the robot. So how the table have a weight when it is in the top of the robot, the center point of the mass certain center point is higher. So how it is higher, then when it moves, then the robot entire the mass will move forward and backward. So if we add more weight in the bottom of the robot, we maybe and have a stable wheels base, maybe it can be reduced, but also I think that with more work in nav2, it can be a lot better. So I did not have much time to work with it because I want to make the presentation, but I think it can be improved even though the physical things.
Yeah, I agree. I agree. Yeah. Okay, so what else? Here, Girish says, "Why do you think the robot stopped before entering the room, and when you needed to give a little help to the robot? Why do you think that happened?"
Before entering into the room,
Yeah, it was
or
like quiet there, and then you moved it a little bit, and then it continued inside the room.
oh, okay, yes, that's the thing of the cost maps and NAP2 configuration, because as you can see, when it left the table, and the road moved back, and it was in front of the table, aiming to the table. You have to rotate like 180 degree, but it keeps rotating in the same direction. In that way, same thing. These two things are NAP2 configuration problems, I think, and I think it can be improved with parameters, configuration, and settings, but it needs a little bit more time to play with those parameters.
Okay. Um, okay, so this one is interesting also from Miguel. So Miguel is asking, from your point of view, what should we add to the system to be commercially viable to use in a real restaurant? So more speed, reliability.
For the entire system means the software and the hardware, or just hardware, or just
Yeah,
software.
both. Whatever you can
But
think of.
for software, it needs for being commercially used, it needs a lot of work, because we need to make sure the robot do not crash with people hanging around. Maybe the cafeteria is pet friendly. If the obstacles are not at the head of the ladder, it can be a problem. Even if let's say something drops and is big, or something is moved. A cafeteria is a place very complicated, because there's always a lot of people. So the system needs to be very robust, to not crash, to not make any losses. And in my case, I think in terms of 100%, my project could be in let's say 40% or 30%. I think that's why. In the case of the user interface, it needs a lot of work and improvements, that like the ones I mentioned before, because you don't have enough feedback of what is doing the robot or the system, and you just have management of the robot picking the table, moving to the back room. But what happens before after the robot moves the table backward? Somebody is going to move the trash can, or we can maybe add a system that move the trash can and put another one clean, and the robot then return the table to the original position. There's a lot of things we can do to make it more robust and commercialized possible, but at least right now is a little bit far from that point.
Okay. Okay, so I'm going to go with the last one. It's not actually a question, but a comment also, because I loved that part where you shared the QR code for or the Docker and so on. I didn't try it. I didn't have the time. But also, after that, you shared a web page at some slide. There was a moment where you
Um,
shared a web page.
a web page, or I don't get it.
Yeah,
Can you be more specific?
in your slides, there, after the QR code and all that, you also shared a web page which was starbots.com or something like that.
Oh no, that are just examples. No,
Okay.
it's not working. Just it's an example of anything. No,
Okay,
it's
okay.
not.
So an idea of how you would do it.
Yes, yes, it have a number and other things, but are just examples.
Okay, okay, okay. Okay, okay, I get it.
Mhm.
Okay, Rómulo, then, yes, so I think we can leave it here. Let me give another applause.
Thank you.
All right, so thanks a lot for the cool presentation. Congratulations for finishing the masterclass. And
Thank you.
yeah, see you around soon.
Okay.
Bye bye, Rómulo.
Thank you. See you.
All right, so I'm going to leave it here. I hope that you enjoyed today's presentations. We are going to have another ceremony in 1 month. It's going to be by the end of June. So we are going to be having these kind of presentations, final project presentation ceremonies once a month, more or less. So the next one is going to be by the end of June with more students, more presentations. So yeah, stay tuned. And yeah, as always, keep pushing your ROS learning. Bye-bye.